Okay, now if you take the rocket, initially let this be ground. So let the rocket be on. Initially, it'll be at the launch pad. So I'll just keeping it on. Let the mass be m0. This is at t equals 0. This is at a ground, that one. Now, so as and what are the forces that will be acting? M0 g and normal contact, or it will be connected to launch pad. So this will be at equilibrium. Now at any time t, the rocket what happens starts lifting up. It ejects gases here. Then the mass of the rocket will be m. So what actually happens here? The fuel of the rocket will be burned too. If you take this is the fuel part. This fuel is what? It will be burnt. So overall mass of the rocket will decrease. Overall mass of the rocket will decrease. Then what I notice is that a thrust force will be acting here. The weight of the rocket, mg, and the fuels will be ejected with a speed vr. So why do this thrust force? Because here there's a ejected gases. That particular gases open, they'll be ejected with a speed. And what is that is a vr, that one. So first we'll define all the things. The fuel will be burnt at a rate. I'll call that as a mu. Mu is equal to what is a mu? Mu is a rate at which fuel is burnt. So usually how do we express this one? Is expressed, it is in burnt. So it will be kgs per second. The unit for this will be 5 kg per second, 2 kg per second, 10 kg per second. That much of fuel will be burnt here. So what is mu? Mu will be kg per second. So this you can write it as dm by dt. There's a typical symbol what I'll be using for that one. Mu, or some books they took lambda, the rate at which the fuel is burnt here. Then what is VR? VR is the velocity of ejected gas, the speed with which gases, the gas being ejected here. Now it just works on Newton's third law. What is the action? I'll ignite the rocket, then the fuel burnt and the gases are ejected. And the gas, it will have some mass, no? It will be ejected. And we know that action reaction should be equal and opposite. As some mass is ejected, a thrust force will be generated. That thrust force will act upward. Now this thrust force, if it is able to overcome the weight, then the rocket is going to accelerate here. Now, what is that thrust force? So now we are going to enter this one. So we know F is equal to dp by dt. So what is the momentum? mv. M dv by dt plus v dm by dt. We have come across situation of this kind where mass of system constant and the speed of that will vary. Now what happened? We are also having a situation where here the mass of system is varying. No? The mass of system varying, this one. So then this particular thing will become, I'll call thrust force here. So what is the thrust force? Ft should be equal to Vr bar dm by dt. Substitute dm by dt with sign. I'll put it plus or minus. There's a basic introduction. As you start working problem, you'll come to know, okay, how to take this one. Now, if the mass of system increases, plus dm by dt. If mass of system decreases, then it will be minus dm by dt. Substitute dm by dt with sign. and this is the expression for the thrust force. Okay, let's come to the rocket propulsion. Say already, like if mass is varying, no, so there's a basic way of thinking on the problem. So what is the thrust force? This VR dm by dt. What is VR? Already we defined velocity of ejected gases. And now this is what with respect to ground or with respect to what it is? With respect to rocket here. What is VR? VR is the velocity of ejected gases with respect to rocket here. Velocity of ejected gas with respect to same thing, conservation of linear momentum. A mass is ejected with a speed, a person will jump with a speed UR relative to the trolley. So there's a basic idea of this one. So like this, we define the thrust force acting on system depends upon the rate at which mass ejected and the speed with which the mass is ejected relative to the system. Okay, let's write the basic equation now after this. Now, what is the basic acceleration equation? The thrust force Ft minus mg equal to ma. This is at any time t. So the equation will be, so now look at that, mass of system must decrease, no? So how to write mass of the system at any time? What is the mass of system? Because if it is initially having 100 kgs per second, then for every 1 second 2 kgs are burnt, then what will be the mass of system? I think go back to a very general idea like this. Let there be 100 kg of fuel. Then what is mu? Mu equal to 2 kg per second. Then after 10 seconds, what is the mass of the system? After 10 seconds, how much of mass is burnt? For every second, for every 1 second, 2 kg. For 10 seconds, 20 kg. Then what is the mass of system? We'll write it 100 minus 20, 80. Can we write a mathematical equation? Mass of system m naught equal to mu minus p. If mass of system increases, mu plus t. So now you see the same 80, I'm going to get it. This one. So this will be 100. This will be 2t. Substitute 10 seconds. At t equal 10 seconds, what is the mass of system? Okay, a bit louder. Can you hear me, all of you?
Yes, sir.
Yes, sir.
Okay, so it's a bit louder. Okay, I'll try to speak it. I think I should adjust my volume. Okay, volume I increased. And now, what is the mass of system at what is the mass of system at any time? So substitute t equal to 1, 2, 3. That particular time you are going to get that one. So this will be VR. Mass of system is decreasing here, no? Minus mg equal to m dv by dt. I'm interested in the acceleration quantity. Oh, let me write one more step. Then I'll go for next year. So what is the expression for acceleration? Acceleration should be equal to minus VR dm by m dt minus t. This acceleration dv by dt equal to minus VR by dt dm by m minus t. So this will become dm by m minus g dt. What is the speed of the rocket? Initially it was at rest, or initially if you have any speed you can introduce that one. So let me initially, because usually rocket what pen will throw, then will launch. Usually at launch pad it will be at rest, no? Most of the cases. So what should be the limit now? The limit should be, if you want, later on I'll change that one, V naught. This will be initial mass m naught at any time m 0 to t. So this will be V minus V naught minus VR log of m naught m minus gt. Simplifying this, v minus v naught minus vr log of m by m naught minus gt. Then v plus v naught. So this will be what is vr. So let me take this. So this will be the speed of the rocket at any time. Initially, the rocket is at rest, put v naught equals 0. Now, if there is no gravity present, then the equation will come. Now, initially rocket at rest. Initially rocket at rest, then v naught will be 0. Then the equation will become vr log m naught m minus gt. Absence of gravity. In that case, the expression will become log of m naught by m. VR will be constant, fix that one. I'll eject the gas at a constant rate, means the VR what happen, that I'll maintain constant. So what is VR? The speed with which gases will be ejected related to rocket here. Now look at this m. What is m? M naught minus mu t, no? This is very important here. So let me write it in a generalized form. M naught minus mu t minus gt. This is the expression for speed of the rocket at any time t. In the absence of gravity, it will become v equal to vr log of m naught minus mu t. And these are the situations will come. So if the mass is ejected continuously, there's a formula is what you should take it. So what is mu? The rate at which mass is ejected continuously. The speed at any time t, this can be determined. You see that one. As t increases, so what should happen to this denominator? Will keep on decrease as t increases. So what do we expect v? V will be continuously increases here. So the mass will be ejected continuously. There's a basic idea, not one time. All of a fuel will not be burnt at launch pad. The fuel will be burnt gradually. So all the numericals what we'll discuss will be like this, where the mass of the system will increase or decrease at a rate. That's a basic idea. If suddenly increases, suddenly decreases, already we have discussed this in conservation of linear momentum. Able to make it out? Please try to, what all you learned, you try to utilize it. Suddenly mass increases, suddenly mass decreases. We know, we have studied in conservation of linear momentum. Here, if the mass gradually increases, gradually decreases, then we are discussing this method. Now, what are the few cases students what happen after this? Like what are very generalized way of thinking this problem? I think some of you, that's for the discussion, what all we made. See, the ejected gas will have some momentum. The ejected gas will have some momentum. Will have momentum, no? Sir, what is the momentum of that? Because continuously the mass is ejected. I should not write here something, sir, mass of the ejected gas. Because the gas will be continuously being ejected. Then what happen in turn? The rocket will acquire momentum. Conservation of, sir, can I apply conservation of linear momentum here? Look at the momentum of rocket, continuously will increase, no? From where this momentum is imparted to the rocket? By the thrust force. Okay, got this? So mass ejected continuously here, not suddenly. I think you should understand. Okay, now let's take some very generalized thinking is what now you should develop here. After this, it's a little bit like mass based it will come. And now there's a rocket.